Hello students. Today continuing with our 1D FEM topic, today we are going to see a thermal load problem. So thermal load problem is that kind of a problem in which you have to consider thermal load along with the external point load given to the system. Okay, in case of self-weight problem, we consider the self-weight of a system along with the external load. In the same way, in thermal load problems, we need to consider thermal loading along with the external point load. So we'll see the example, we'll solve the example, and then the concepts of this type of a problem will be seen during the solution. Now the problem is that this is a step shaft. Okay. The first step is made up of brass, the second step is made up of aluminium, and third step is made up of steel. So three different steps of three different material. The length of the brass member is given 850, that of aluminium 650, and steel 450. These are the physical values of brass, aluminium, and steel are given. That is area, cross-sectional area, Young's modulus, and this is the thermal diffusivity. So this is what? Thermal diffusivity. Okay. So whenever there is thermal diffusivity is given, that means you have to consider the thermal load for solving this kind of a problem. In the same way, like while calculating a self-weight example, if the density is given, that means it is rest assured that you have to consider the self-weight of a system. In the same way, if the thermal diffusivity is given, that means you have to consider thermal load. Okay. Then there are two loads. Two external point loads are applied. This is P1 and the magnitude of this P1 is 65 kilonewton, and second one is P2 and the magnitude of P2 is 75 kilonewton. Okay, and the structure is subjected to increasing temperature of 70 degrees Celsius, delta T equal to 70 degrees Celsius. So this delta T is the difference of the ambient temperature and the temperature of this step shaft, and that difference is given 70 degrees Celsius, means the ambient temperature is 70 degree higher than the temperature of this step shaft. Okay. So this step shaft system is exposed to some high temperature, 70 degree high temperature. So because of exposing this system to a high temperature, obviously the temperature of a system will get increased, and because of that thermal load will be developed, thermal stresses will be developed inside this system. So in this example we are going to see how this thermal load can be included along with the point load for solving or for finding the field variables such as displacement, stress, and reaction. Okay. So our first step is, we'll see the solution. First step is discretization. So in discretization, we will discretize it into three elements. This is element number 1, this is element number 2, and this is element number 3. Element number 1 means brass, element number 2 means aluminium, and element number 3 means steel. The loads are load number 1, 2, 3 and 4. Okay. Similarly, U1, F1 is the displacement and force at node number 1. This is U2, F2, U3, F3, and this is U4, F4. Okay. So this is a discretization. Now the element stiffness matrix. Second is element stiffness matrix. So we calculate the element stiffness matrix for first element, that is A1 E1 by L1, 1 minus 1 minus 1 1. Okay, we'll put the values here. A1 is given 2450 multiply by the Young's modulus of the brass member is 83. 83 is GPa, so convert it into Newton per mm square, so it is 10 to the power 3. Divided by length of the member is 850. It is 1 minus 1 minus 1 1. So the answer of this expression comes out to be, if 10 to the power 3 is outside the bracket, then inside the bracket is 239.23 minus 239.23 minus 239.23 239.23. We'll give the row number, column number to this. So this is row number 1, row number 2, column number 1, column number 2. So since K1 is made up of, element number 1 is made up of node number 1 and 2, so we give the row number, column number as 1 2 1 2. Similarly, we calculate K2 and K3. So K2 is, so I have calculated K2, 10 to the power 3 outside the bracket. It is 134.61 minus 134.61 minus 134.61 134.61. And element number 2 is made up of node number 2 and 3, so give the row number, column number as 2 3 2 3. Similarly, K3, K3 is 10 to the power 3 outside the bracket. It is 288.88 minus 288.88 minus 288.88 and 288.88. And the row number, column number will be 3 4 3 4. So these are the element stiffness matrix. From this element stiffness matrix, we find out the global stiffness matrix. So we'll find out the global stiffness matrix here. So next step is global stiffness matrix. So Kg, global stiffness matrix, 10 to the power 3 outside the bracket. It will be 4 by 4 matrix, 1 2 3 4 1 2 3 4, and the values will be 239.23 minus 239.23 0 0 minus 239.23. Add this 2 2, there will be two values, that is 239.23 and 134.61. So total becomes 373.84, and then it is minus 134.61. This is 0, 0, minus 134.61. Now at 3, 3, there are two values, so it becomes 423.49, and then minus 288.88, 0, 0, minus 288.88, and 288.88. So this is a global stiffness matrix. Okay. So up till now, the problem is very routine, and everybody know how to find out the global stiffness matrix. Now next step is to find out the global force matrix, because to apply principle of minimum potential energy or Rayleigh-Ritz method, we need global force matrix and global stiffness matrix ready with us, so that we can find out the values of global displacement matrix. Okay. So next we will make our global force matrix ready. So global force matrix. Now we know that global force matrix Fg, it will be a combination of the external load matrix plus the thermal load matrix. Here this TL means thermal load. Okay. Now first we find out thermal load, because external load matrix can be easily find out by using the values given of 65 kilonewton and 75 kilonewton. Now we find out the thermal load matrix. Okay, thermal load matrix, that is FTL. Now this FTL, it will be thermal load in element number 1, thermal load in element number 2, and thermal load in element number 3. So this total thermal load matrix will be a combination of thermal load in element 1, thermal load in element 2, and thermal load in element 3. So it will be thermal load in element 1 plus thermal load in element 2 plus thermal load in element 3. Okay. So first we find out thermal load in element 1. So how much force is exerted to element number 1 because of exposure of this system higher than 70 degree, means exposure to this system whose temperature is more than 70 degree more than the temperature of this shaft. Okay, so that is calculated by E into A into alpha into delta T minus 1 1. Okay. Now this is element number 1. This is element number 1. Why it is given? This is for node number 1 and 2, because this element 1 is made up of node number 1 and 2. So this is a formula for finding the thermal load of element number 1. Now consider this is a brass member or element number 1. Okay. Now this is our node number 1. This is our node number 2. Now this is exposed to a higher temperature. For example, heat is supplied here. Okay, this is a burner. Consider this is a burner and you are heating this element. Now obviously because of the heat, this brass member will expand. This brass member will expand. Its length will be increased. So obviously there will be a tensile stresses, tensile thermal stresses in this brass member. That means the load which is acting will be axially opposite direction. So this load will stretch this member in this direction, and because of this thermal loading it will stretch the member in this direction. So this brass member will get stretched. That means the load will apply opposite to each other. So this will stretch the member in this direction, this will stretch the member in this direction. At node number 1, the force is applied towards negative x-axis, and at node number 2 it is applied in positive x-axis, and that is why here -1 and 1 is given. So -1 means this thermal load will act in negative direction, and here the positive sign indicates that this thermal load acts in a positive direction. So at node number 1 negative, at node number 2 positive. Okay, so this is the formula for finding the thermal load in any element. Now we put the values. Now first we balance the units. Okay, so what is the unit of the Young's modulus? It is Newton per mm square. The area's unit is mm square. Thermal diffusivity alpha, alpha का unit क्या है? Per degree Celsius, means per degree Celsius. And delta T is 70 degrees Celsius. So degree Celsius. So here mm square get cancelled, degree Celsius get cancelled. So answer will be in Newton. Okay. So this is the thermal load which is applied to element number 1. Now we put the values. Now E is what? E is 83 GPa, that means 83 into 10 to the power 3. Area is given as 2450 multiplied by alpha. Alpha is 18.9 into 10 to the power minus 6. 18.9 into 10 to the power minus 6, and delta is 70 degree multiplied by 70. And this is -1, 1 for node number 1 and 2. And if you calculate the answer of this expression is 269.03 into 10 to the power 3 minus 1 for node number 1 and 2. Okay. Now this can be written as 10 to the power 3 outside the bracket. In the bracket it is minus 269.03 and 269.03. for node number 1, 2. In the same way, we calculate the thermal load matrix for element number 2. This is thermal load matrix for element number 1. Similarly, the thermal load matrix for element number 2 is calculated as 10 to the power 3 outside the bracket, and it is minus 140.87 and 140.87. This is for node number 2, 3. Similarly, the thermal load matrix for element number 3 is calculated as 10 to the power 3 outside. It is minus 106.47, 106.47, and this is for node number 3, 4. So same way EA alpha into delta T. So put the values of aluminium. You put the values of aluminium, you get the thermal load matrix for element number 2, and put the values of steel member, you will get the thermal load matrix of element number 3. Now from this thermal load matrix 1, thermal load matrix 2 and thermal load matrix 3, you can make a global thermal load matrix. A global thermal load matrix which will be 1, 2, 3 and 4. So from these 3 matrices, this is 1, 2 and 3. From these 3 matrices you can easily make the global thermal load matrix. So 10 to the power 3 outside the bracket. So inside the bracket node number 1 पे कितना है वैल्यू, एक ही वैल्यू है, that is minus 269.03. Similarly, at node number 2 there are two values, 269.03 minus 140.87. So plus minus. So if you do the calculation, it will be 128.16. Okay. Similarly, at node number 3 there are two values, plus 140.87 minus 106.47. The answer is 34.4. And at node number 4 there is only one value, that is 106.47. So in this way, from the individual element thermal load matrix, we have made a global thermal load matrix. So in thermal loading, along with the thermal load, we have to consider the external load as well. So now we will make a global external load matrix. So this global thermal load matrix we have calculated. Now this external load matrix we will find out, and then we add both these matrices to find out the global force matrix. So next is external load matrix. Now external load matrix is for node number 1, 2, 3, 4. Okay. So at node number 1 there is no external force, so it will be 0. At node number 2 there is P1 is 65 kilonewton in negative direction, so it will be minus 65 kilonewton, so 10 to the power 3 outside the bracket. And at node number 3 there is 75 kilonewton in negative direction, so minus 75. At node number 4 there is no force, 0. Okay. Now add both these forces to find out the global force matrix. So the global force matrix will be at node number 1 0 minus 269.03, so answer will be minus 269.03, 10 to the power 3 outside the bracket. So don't forget this 10 to the power 3. If you miss this 10 to the power 3, your entire calculation will get wrong. At node number 2 it is minus 65 plus 128.16, so the answer will be 63.18. And at node number 3 minus 75 plus 34.40, it will be minus 40.6, and last 0 106, so answer is 106.47. Now this is our global force matrix. Now we are ready with global force matrix, we are ready with our global stiffness matrix. Now we can apply the principle of minimum potential energy. Okay. Now next step is to apply So step number 4, apply principle of minimum potential energy or Rayleigh-Ritz method. Okay, so which says that the global force matrix is equal to global stiffness matrix multiplied by the global displacement matrix. Now global force matrix is this one, 10 to the power 3 minus 269.03, 63.18 minus 40.6 and 106.47 equal to 10 to the power 3. This is the stiffness matrix, 239.23 minus 239.23, 0, 0, minus 239.23, 373.84, minus 134.61, 0, 0, minus 134.61, 423.49, minus 288.88, 0, 0, minus 288.88, 288.88. And then the global displacement matrix, that is U1, U2, U3, U4. So this is our we have applied the PMP. Now we apply the Gauss elimination method or Gauss elimination technique. So apply Gauss elimination technique. So Gauss elimination technique says cancel out the rows and columns for the fixed nodes. So here node number 1 and node number 4 are fixed. So cancel out row 1, column 1, row 2, column 2, and from the remaining portion you calculate the values of u2 and u3. So u2 and u3 is calculated as u2 comes out to be 0.15 mm and u3 comes out to be minus 0.049 mm. Okay. So here this node 2 has a positive displacement and node 3 has a negative displacement. So even if there are two external load which forces the nodes towards negative direction, but because of the temperature effect, node 2 shows positive displacement. Node 2 is moving against the application of load, okay, whereas node number 3 is moving along with the external load. Okay. Now we are ready with the nodal displacements. Then you can easily find out the stresses in each element and reaction at the support. The rest of the process is very similar. So hope you understand how to solve this thermal load problem. So thank you very much.